Okay, I believe we're now actually live. Question is, where are we in terms of the delay of this? Okay. All right. Um, I apologize to everyone. We had some technical difficulties in terms of getting the stream set up. We're still very new to this, so thank you for being patient. Um, Welcome everyone for coming to this event tonight. This is Universe at Home. This is the first official one in a series of events. Um, my name is Trevor Knuth. I will be the primary host of the talk tonight. I am being joined by Hayley Williams and Laura Salo. Please introduce yourselves.
Hi, everybody. I'm Hayley. I'm a second-year graduate student at the University of Minnesota, and I'm currently studying gravitational lensing, which basically just means how giant objects in space warp light that goes around them. So something very different from the sun.
And then Laura.
Hi, I'm Laura, and I am a second year graduate student also at the University of Minnesota, and I am currently looking at galaxies.
And then once again, my name is Trevor. I'm a fifth year astrophysics graduate student at the University of Minnesota, and I am studying the sun, which is the focus of our talk and our presentations tonight. A little bit about Universe at Home, and kind of why we're doing this. So in years past, we ran a program called Universe in the Park, which was based on a program done by the University of Wisconsin-Madison. Their graduate students ran a same program in the state of Wisconsin. It was really successful. We adopted it here, and we always really enjoyed having these events in the summertime. Obviously, with the pandemic, we can't have those events this summer, and so we've been working hard to kind of sort of figure out how to have these events in a virtual setting. And that is where Universe at Home came into being with a lot of work from a fellow graduate student named Nico Adams. Um, Tonight's itinerary is going to be a talk called The Sun is a Star. Sun's journey from an object of worship to our gateway to the stars. Following that, we will have a Q&A. So feel free to use the YouTube chat to ask questions. Laura will be moderating the chat and making sure that these questions are accumulated. And then following the Q&A, we'll be going into a interactive session where Hayley will be showing you a couple of really interesting sites that relate to actually observing real solar data from satellites, as well as space weather models, which we'll talk about a bit later. And these are sites that anyone can access for free. All right, now let me just get this going, hopefully. All right, so hopefully everyone can see that just fine. All right, so the point of the talk tonight is called The Sun is a Star, the sun's journey from an object of worship to our gateway to the stars. So here we see a beautiful image of the sun and all of the wave bands of AIA, which is an instrument on board the Solar Dynamic Observatory, which I'll talk a bit about that later on. The goal of this talk is that as somebody who studies the sun, it oftentimes is sort of viewed as the enemy of astronomy because you want to see the stars and the galaxies, and the sun basically just gets in the way of all of that. And so I wanted to take this as an opportunity to sort of show the history of the sun and kind of how it sort of really made it so that we could actually study stars to begin with. And so first, I'm going to talk a little bit about the sun in general, some things that are important to know and sort of fun facts to have. Then I'm going to go and talking about how ancient cultures viewed the sun. From there, I'll go into how those views of the sun went from sort of an object of worship to actually starting to consider it as an actual physical thing and connecting it to the stars. And finally, I'll talk about solar physics today and sort of how do we actually study the sun every day in the year 2020. All right, so the sun at a glance. So the sun is a very, very massive object, of course, because it is a star. Its mass is 2 times 10 to the 30 kilograms, which is sort of a nonsensical number in itself, but compared to Earth, it's over 300,000 Earths packed into it. So this is a massive object that accounts for 99.9% of the mass of the solar system. So all of that is concentrated in the sun, and the rest of it is kind of dust floating around it. The radius of the sun is 700,000 kilometers. That corresponds to 109 Earths. If you see this image here, imagine the center of it, 109 Earths to go from that center out to the outer edge. It is about 150 million kilometers away. There isn't really a very good way of sort of depicting that, other than it's about 200 some times the radius of the sun. But importantly, it takes light, one of the fastest thing in the universe, over 8 minutes to reach Earth from the sun. That's how far away it is. And comparatively to the rest of the universe, that's extremely close. The sun is about 4.6 billion years old. An interesting thing, the sun is a little bit older than the Earth. That is because the sun formed, and when the sun formed, started to blow away all the dust in the protoplanetary disk. But planets kept forming after the sun had formed. So you usually see estimates of the planets being a little bit younger.
Hey, Trevor.
Yep.
Just so you know, everybody is seeing the presenter mode.
Oh.
I don't know if you want to try to change that. I don't think it's a huge deal, but if you want to.
I will try to change that. Thank you. Let's do a new share. Is that better? I think it should be better.
Yes.
All right. Apologize for that. Once again, we are still exploring this new virtual medium. All right. And then finally, the star type of the sun. So people might not know this, but all stars have a astronomical typing to them. The really biggest, brightest stars are called O stars. And then going dimmer, you have B, A, F, G, K, and M. Now you might be thinking to yourself, that is just a random jumble of letters, and you would be right. See, astronomers have this really hard habit of when something is set, is never changed. We really like historical conventions, unless they turn out to be wrong, in which case we will change them. So how we actually remember that long string of letters is O, be a fine girl or guy, kiss me. So we have to use all kinds of techniques to remember all this information. So what does the sun being a G2 star actually mean? So the letter refers to the temperature of the star. And the Roman numeral, the V here, the 5, is the size class. So though the sun is not a white dwarf star, it's actually considered to be a dwarf size star. All right, let me move on. What is important about the, there we go, the fact that it has that G-type star is that the radiation, the color of the light created by the star, is determined by its temperature. And so here we have a picture of a rainbow, which is a spectrum, or a distribution of colors of what the sun creates. This is the visible light of the sun only because it happened to be what the sun produced. So let me say what I actually mean by that. So because the sun is the temperature that it is and the color that it is, plants evolved to be green. So plants are full of chlorophyll, which is designed to absorb the radiation coming from the sun. If the sun had been hotter or cooler, plants would have actually evolved in a very different way in order to actually be able to absorb the radiation from the sun. And similarly, eyes. You and I all have eyes that are used to actually observe the space around us. Basically, they are just photon detectors. And our eyes are designed to see a very specific band of colors of light. We see those bands of colors of light because that is what the sun produces, because it has a particular temperature. And so all these different amazing eyes that exist around nature all evolved to be able to see the specific color of light that the sun creates. And so even before humans ever came about, the sun was already having a large impact in terms of how life behaved on Earth. All right, so what did people think of the sun when they started to form their own civilizations and cultures? So this is a quick sort of smattering of different ancient cultures. In the ancient land of Egypt, they had the god Ra. Ra was the ruler of all creation. He was a very powerful god and kind of the chief god in their pantheon. He was depicted as a human with a falcon head on top. In the Greece and Rome cultures, the Greeks called the sun Helios, the Romans called them Sol, and he was shown to be an all-seeing being, oftentimes one who sort of found out information that was hard to know, kind of sometimes called the Eye of Zeus. Because remember, Zeus or Jupiter in Rome was the god of the sky, and the sun resided in the sky, and so it was a very powerful aspect of sort of the chief god Zeus's domain. In China, this is an interesting story that I found. The Chinese god of the sun is Rigong Tai Yang Qingjun. This is, of course, a subculture of ancient China. In their myths, he was actually one of 10 suns. Because there were 10 suns, they made the earth far too hot. And so a mythical hero, Hu Yi, shot down 9 of the suns, leaving only the one that still resides up in the sky. And this is an interesting story because it does show that the sun can sometimes have a disastrous or negative effect on Earth. It can cause things like droughts. The weather patterns show up as such. Later on, we'll learn about space weather. The Inca people, it was Inti, the protector of the people. So it's a very sort of close, sort of very personal relationship with the sun god. And he's actually still on the Peruvian flag. So Peru is where the Inca people resided. And they still sort of show their connection to those old roots by having them on the flag. And of course, many, many more civilizations around the earth all has sort of a place of honor or worship about the sun because it was such an important thing in ancient culture and society. It seemed to be what set the seasons. It was how you grew crops. It's how you saw during the day, created the day and the night. So people recognized it as being really important. Because it had this important, people oftentimes built structures designed to record special dates for when the sun seemed to be moving around the sky. Things like the equinoxes or the solstices were created. Here we have temple. This is the famous Sun Temple in India. On the top right is Stonehenge in the UK. The bottom left, I believe, was a Sun Temple in Egypt. And then down in the bottom right is a clay tablet of showing different sort of astronomical observations. So because the sun had this sort of really important place within ancient cultures, it means people looked at the sun a lot. Hopefully not so much to hurt their eyes, but it means that they were always watching it and seeing what it was doing, which meant that over time, they started to figure out more and more information about it. So the first people to kind of start to figure out, hey, maybe the sun isn't this divine ethereal object were the ancient Babylonians. We figured out that the sun's movement wasn't uniform. There were kind of little wobbles and wiggles and sort of how it moved about. Sort of people I would go through time. Different people started to estimate that the sun had a physical distance to the earth. There wasn't some ethereal plane separated from it. Others began to postulate that maybe the earth even revolved around the sun. People began to figure out things like that there were sunspots. So in 1100 to about 1200 CE, people began to actually see that there were these dark regions of the sun that would darken and then disappear. And of course, famous astronomer Nicholas Copernicus created the first mathematically detailed heliocentric theory. That just means the idea that the Earth is a planet revolving around the sun. Before that, the common theory was geocentrism, which was that the sun was an object revolving around the Earth. As we kept going, the sort of Galileo Galilei. Galileo was considered the founder of modern astronomy. He was the first one to sort of use a telescope to make observations of space. And one of the things that he used was he just detailed sunspots on the sun, how they came, how they disappeared. You can actually see this is a drawing done by Galileo of different sunspots on the sun. And he believed that they were actually on the surface of the sun. He also did a lot of observational evidence that would go on to support Copernicus's idea that the Earth was revolving around the sun. And then finally, Isaac Newton observed the spectrum of the sun. So rainbows had been around for a long time, but people didn't necessarily know the connection between rainbows and the sun. However, Isaac Newton, using different prisms, uh, concluded that white light coming from the sun is actually a combination of all the colors of the rainbow. It's actually the sun creating the rainbows to begin with. All right, so over these hundreds to thousands of years of people observing the sun meticulously, they created their calendars by it, their clocks by it, they planted their fields by it. They started to understand that the sun was not this ethereal being, was actually a physical object. And because it was now a physical object, there were a lot of questions that people had about the sun, such as what were these strange dark spots? Why was it so bright and hot? It's an extremely bright, extremely hot object. What's powering that? What's it made of? Right? It seems like it's a bright, burning ball of fire, but is it really? And how old was it? So when did the sun actually get created? And finally, what's the inside of the sun like? What's going on inside of it? Right. So the first thing I want to talk about in terms of the modern solar physics is the Carrington event. So Richard Carrington was an astronomer, was an amateur astronomer observing the sun. In 1859, he was watching some sunspots. And here we see a picture of sunspots, which are these really dark regions of the sun. They're still very, very hot, but they're dark because they're just comparatively cooler than the rest of the sun around it, so they appear dark. And what Richard Carrington saw with these sunspots in 1859 was that they actually got brighter near them. That's not usually what happened. The sunspots got dark and then disappeared. And so the next day, after seeing this weird brightening, and this is actually the recordings that Carrington made, there was a massive geostorm near Earth. A geostorm is when energy and plasma from the sun slams into the Earth's magnetic field and creates a lot of interesting phenomena. So aurora, the northern lights, they were observed as far south as Cuba, where usually you have to be, kind of in Canada to be able to see these. They got really extended far south. And telegraphs, this brand new invention that allowed people to communicate over long distances, suddenly had all of this weird noise and interference. So people decided to just unplug the systems entirely, only to find that they were still operating without any power source. So this is what a really weird event. And what he actually was observing was a solar flare and the resulting coronal mass ejection. So hopefully this video plays and I can put this on loop. All right. So what you're going to be seeing in this video are these coronal loops, and here we see a beautiful flare going off. So flares are these massive explosions on the sun. They release energy equivalent to 1,000 to 100 million times larger than the solar bomb, but the biggest bomb humanity has ever built. So these are really powerful, energetic things. If you look at this, the Earth is a tiny fraction of these loops. These are explosions literally larger than the size of Earth. Sometimes when these explosions go off, they throw these huge chunks of plasma out into space. And we call these coronal mass ejections, or CMEs. So Carrington's event, seeing these dark sunspots get really bright and then having all this weird activity happen on the Earth, paved the way for solar terrestrial connections. That is, this is the first time that we on Earth began to understand that changes on the sun have a very direct and real impact on Earth. Before that, the sun was a very, very constant thing. Its position in the night sky appeared to change, but really the amount of energy it gave to the Earth every day was the exact same, it seemed. However, we started to see these really weird things because of what the sun was doing. And so we further understood this because in the 1950s and 60s, America started launching spacecraft. And these spacecraft carried little probes that had interesting instruments on them. So here we see Explorer 1. This was the first scientific spacecraft ever launched into space. And it had a little Geiger probe on it. What this Geiger probe did is it measured radiation and energetic particles. And this center guy here was Dr. James Van Allen. He was the lead scientist on this project. What they discovered was a belt of radiation surrounding the Earth. And these were named the Van Allen radiation belts in his honor. And so we didn't know or expect that there would be anything like this surrounding Earth, except for the fact that we began to understand that the sun had a stream of plasma coming off of it that would interact with the Earth and create these things. So we started to see that there was actual structure around Earth being caused by the sun. And so this whole process of coronal mass ejections and flares creating these geostorms on Earth is what we call space weather. Originally, it didn't matter because we didn't have any effects that could impact us. Over time, though, we developed things like air travel, radio communication, power grids, and satellites in space flight. And all of these are systems that can be impacted by space weather. So it started to become a very, very important thing that we knew and understood what space weather was and how it was happening. And so we started to develop high-tech ways of actually observing that. So here is a coronal mass ejection, or two of them coming off of the sun. So here you saw one giant one belch off to there, and here another one belched off the front, the top. Here we see sort of further back, the coronal mass ejection kind of coming out. So it became very important that people started to understand what space weather was. We need to understand what solar flares were, understand what coronal mass ejections were, what the solar wind was, and how all these things interacted. And the result of all of this understanding was SWPC. The SWPC is the Space Weather Prediction Center. This is operated by NOAA, the National Oceanic and Atmospheric Administration, and they are literally space weathermen. So they are people who use high-tech models and observations to see what the sun is doing and predict the weather in space near Earth. And they use these sort of predictions to decide things like when can astronauts exit the spacecraft and actually do things like spacewalks? When can pilots have flights that go over the poles of Earth? They also figure out things like, is there a storm that might impact power grids on Earth? And if so, they need to tell the power companies about that so they can take extra precautions against it. And so that is one avenue that people really wanted to explore a lot as they sort of got into modern astronomy, which is what these dark spots were and what was it that happened after Carrington saw those sunspots get really bright. Another really interesting thing was, how old is the sun? So this is kind of a personal favorite story of mine because it was a battle of the sciences. And so at the time, science was having a hard time figuring out how old the Earth and the sun were. And so there ended up being a battle where on one side was astronomers, and the other side was geologists and biologists. You see, biology and geology had reached a point where they started to understand certain processes that took hundreds of millions to billions of years to happen. Things like evolution and plate tectonics, creating the geological structures we see, would take an immensely long period of time. However, astronomers, we weren't so convinced because we didn't know where the energy of the sun was coming from. See, we tried a lot of different ideas. We thought, well, maybe it's a giant burning chunk of wood. Maybe it was burning coal. Maybe it was liquid heat radiating off of it. We tried a lot of different ideas, but basically, all of them could only come up with a lifespan of tens of millions of years. So we had this really weird conundrum where astronomers knew the size of the sun, they knew how bright it was, and they figured that no energy source we knew of could power the sun for longer than billions of years. And so these geologists and these biologists saying billions of years, we had no idea what they were talking about. However, nuclear physics came to the rescue. In the early 1900s, several scientists started to figure out the idea of nuclear fusion. What nuclear fusion is when particles go really fast and slam together, they can actually stick. So here we have hydrogen particles coming together to create a heavy hydrogen particle. This whole process is called nuclear fusion because they're fusing together. When they do that, they release this energy. Actually ends up being quite a lot of energy. This process is far more efficient than anything else we've ever known, and is actually more efficient than anything that we can still to this day do. nuclear fusion is sort of one of the holy grails of science and engineering, where if we could create sustainable reactions on Earth, we could solve the energy problems of Earth forever. However, it's a really difficult thing to do. But with this process sort of figured out, astrophysicists can now confidently confirm that the sun was on the order of 4.6 billion years old. They were now in perfect agreement with what the geologists and biologists were saying. Now, the other effect of knowing the nuclear fusion process going on inside the sun was we began to understand what's happening inside other stars. So, this is what we call a Hertzsprung-Russell diagram. Here are those funny letters talked about earlier, the O, B, A, F, G, K, M. On this diagram, what you see is to the left are really, really hot stars. And then as you go up are really, really bright stars. So over here are red supergiants. These are stars that are massive, massive stars, but they're very, very cool stars. Down here, we have the red dwarfs. These are stars that are really, really cool and really small. Up here are those O stars. Those are the ones I said were really hot and bright. And then down in here is the sun. As I said before, sun is a G25 star. That means that it is relatively an average star. It's not as big and bright as these, but there are a lot of stars down here that are a lot smaller than the sun. And so figuring out things like what the physics inside of stars was meant that we could start to figure out things like how the size, temperature, the luminosity or brightness, and how old stars are all work together. And starting to figure out things like the processes that were driving the insides of these stars meant that we could figure out how stars formed, how they evolved, and eventually how they would die in massive fiery explosions called supernovae. And so understanding and studying the sun is what allowed us to actually begin to understand the stars and create things like the Hertzsprung-Russell diagram, which is a really, really powerful and important form of studying stars. So where is solar physics today? So back in the mid 2000s, NASA launched a program called Living with a Star. This program was aimed at developing and launching several spacecraft which would study the star and the Earth, or the sun and the Earth, and the Sun-Earth connection in heavy detail. So these included launching what are called the Van Allen probes, the Solar Dynamics Observatory, the Parker probe, the Solar Orbiter, and the SET experiment. And in particular, the Van Allen probes and the Parker probe have heavy University of Minnesota involvement. We have a PI of one of the instruments of the Van Allen probes. The probes have now completed their lifetime mission, which they're very, very successful in. And the Parker probe is ongoing right now. So here in the top left, we have the Van Allen probes. These were two twin spacecraft who were designed to fly through those radiation belts we talked about and basically measure the properties of them. Here we have the Solar Dynamics Observatory. This is a massive, massive spacecraft. Basically, if you have seen a pretty picture of the sun in the last 10 years, the odds are it was created by this spacecraft here. Down here, we have the Parker probe. This is a spacecraft that is currently undergoing its science mission. It is designed with this massive heat shield to get as close to the sun as humans have ever gotten. I believe as far as 10 solar radii away, which is extremely close because the sun is very, very hot, very bright. So it's hard to get any piece of instrument really close to the sun. So a lot of cool and interesting things that are happening with this spacecraft where you have these booms going out, and one of its instruments, sort of this little camera, that's kind of like peeks around the heat shield, takes pictures as it flies through the corona. And then finally over here, we have the Solar Orbiter. This is actually a mission that is primarily being operated by ESA, the European Space Agency, basically Europe's version of NASA. This launched, I believe, February 2019. And so it is currently going on its journey from the Earth orbit to the sun, and it will begin its science missions late next year. So because it takes a long time to make a spacecraft get close to the sun, it is currently in transit. And then SET is a experiment to sort of study various forms of the near-Earth environment in ways that the Van Allen probes failed to do. All right, thank you for listening. We'll be able to take questions now. So if you have any questions that related to this talk, free to ask them. But beyond that, any questions that you have about space, astronomy, science, academia, any of those questions, we'd love to take them.
Trevor, we have a few questions from Ksenia Kravchenko. She asks, how did astronauts find out how hot the sun is?
Oh, that's a really good question. And there are a variety of ways to figure it out. But the way that scientists do it today is that they do what's called a black body spectrum. So basically, everything in nature is emitting radiation. You and I are emitting infrared radiation because we're relatively cool compared to the sort of how hot things get in the universe. And so you can look at the light coming off of the sun and you can sort of spread it out by color. So similar to a rainbow, essentially, and basically compare those colors the sun is creating and compare it to a mathematical formula. That formula will actually tell you how hot the sun is, which coincidentally, it's about 5,800 Kelvin, which compared to the temperatures on Earth of about 300 Kelvin is extremely hot.
We have another question from Jam Moore, who asks, what color is the sun, and what will happen if I stare at the sun?
Right. Well, funnily enough, the sun is actually all colors. So that's sort of the weird thing about a black body radiation is that anything that is hot and dense is technically emitting in all wavelengths. The peak wavelength of the sun, the color that it emits the most of, is right around the wavelength that we associate with the color green. So we see the Earth, sun, as being yellow because our eyes have evolved to see the different wavelengths of the sun in such a way that we perceive it as yellow, but in reality, the primary color coming from the sun is green. In terms of staring at the sun, I don't know if full blindness happens. I do know that you can do serious damage to your eyes if you look at the sun for too long. So please do not do that.
Our next question is from Ksenia Kravchenko again, who asks, what is the biggest...
I think you cut out, Laura, after biggest.
Okay, we're asking about the biggest star.
Oh, the biggest star. Okay. So the biggest star that I believe we know of, and there may be even bigger stars now, is VY Canis Majoris. Essentially, these are what are called supergiants. So these are stars that are already very, very massive. They get very late into their life. And as they get really close to death of a star, they can start to inflate to these extreme sizes. Even the sun, a relatively small star, will get so big towards the end of its life that its size will go out to about the orbit of Mars. So it'll become a very, very huge star. These stars, these supergiants, are actually so big they could envelop the entire solar system very easily.
We have another question from Aaron, who asks, what kind of damage could a very large solar flare do?
Great question. So as I mentioned earlier, the Space Weather Prediction Center and those who study space weather are studying it because space weather can have a very real impact on our day-to-day lives. And in the case of a worst-case scenario, which is a big coronal mass ejection comes off of the sun, hits Earth, and can put its energy into the magnetosphere of Earth, a lot of damage can happen. A event very similar to this happened in 2012 where it just missed us. We'll be seeing more on that in Hayley's activity later on. But what this storm could do to Earth if it hit us is it would actually create what's called a ground-induced current, which is basically it would take anything that's large and conducting, like power grids, it would drive really large electrical currents through it, which if you're not expecting large electrical current, they can cause a lot of damage. In particular, transformers are really susceptible to this. Transformers are objects which take voltages from two different power lines and basically make the voltage go from one voltage to another one. And they could get basically superheated and destroyed by these huge currents created by these geostorms. Were that to happen on Earth, so say that 2012 event, kind of a worst case scenario, it would basically knock out the entire power grid of America and create trillions of dollars of damages in our infrastructure. And so people are very, very interested in sort of whether or not these storms are happening, could they happen, and how to actually prevent the damages from happening should they occur. I also believe 2003 there was a blackout in Ontario, which was due to a solar storm.
Our next question is from Rebecca, who asks, where is the Parker probe now?
That's good. I actually don't know where it is right now. I believe it has done its sixth, what we call closest approach. So the orbit of Parker probe is a really big ellipse, which is like a large oval. On one side is really close to the sun, while the other side is really far from the sun. And so when it gets really close to the sun, it goes extremely fast. That's when it actually goes into the corona. And so I know it has done at least 6 of these really close to the sun passes so far. I believe it may be starting to get ready for a 7th one, but I'll have to check on that.
We have another question from Ashwath, who asks, how does one measure data such as mass and other parameters?
That's a good question. So I guess it depends on what object you're looking at. For instance, the planets and the moons in the solar system, we figure out the mass by studying their orbits and looking at the equations we know about how gravity works to figure out what the masses must be. For other stars, it can be a really big challenge because they're so far away. You have to use things like those color diagrams. Let me go back to that. So these Hertzsprung-Russell diagrams, where if you see a color of a particular star, so you look at its spectrum, figure out how hot it is, and how bright it is, and how far away it is, you start to figure out how big it must be and how massive it must be. Because again, we understand all of the physics that are happening inside of stars. We know the fusion that's happening, we know how plasma convects, heats, and cools, and so we can figure out the relationships between all of these different parameters to figure out how massive these stars must be. And then for galaxies, it's a similarly difficult thing where you have to use things like ratios of how fast galaxies are spinning to how bright they are to figure out their mass. Although I'm sure Hayley or Laura could answer more about how you figure out the properties of galaxies.
Hayley, would you like to add anything?
Yeah, sure. So in terms of if you're wondering about how we measure the mass of galaxies, that's something that's, a lot more complicated because we're looking at something that's much, much larger than a star and much, much further away than a star that we would be looking at in our Milky Way galaxy. So there's different methods for that a lot of the times can get very mathematical and model-based. But different things that we look at are like how fast the galaxy is rotating, And also what I mentioned when I introduced myself was gravitational lensing, which basically means that really, really massive objects can actually bend light. So if we measure how much the light that we're seeing from behind a galaxy is bent, we can make some comments about the mass of that galaxy. But in general, it's a lot more difficult to constrain what the mass of a galaxy is compared to a star, especially a close star like the sun. So a lot of the times we're just coming up with our closest estimate to what we think that mass is.
Great. We have another question from Ben Lee. He's got two questions here that are related. The first one is he would like us to talk about the corona paradox, and then he's also wondering what the coronal heating theory is.
Okay, so it's a great question because the corona problem is a ongoing kind of one of the big mysteries with the sun. Basically, if you look at, go to, let's go to here. All right. So what you're seeing surrounding this picture right now is the corona of the sun. The corona is this really sparse, extremely hot plasma that's kind of enveloping the sun. You can think of it as sort of the atmosphere of the sun. Similar to Earth's atmosphere, the sun has its own atmosphere. That's the corona. When you look at the surface of the sun, so where these sunspots exist, what we call the photosphere, that temperature is about 5,800 Kelvin. And so, I say compared to Earth, that's really hot. But the corona, meanwhile, is on the order of 3 million Kelvin. So it gets extremely, extremely hot. And that's something that doesn't make sense. If you're really close to a campfire, you have to walk away from it. You don't feel hotter, you feel cooler. And so what that tells us is that there has to be something happening on the sun that creates all this heat and energy that goes into the corona. The coronal heating models, there are two sort of major models. One is the flare heating model. So those giant explosions that we see happening on the surface of the sun, called solar flares, we know those release a large amount of energy. And so one of the models is that perhaps those are releasing enough energy to heat the sun up to these extreme temperatures. The other is called the wave heating model. Basically, on the sun, you can have all kinds of waves: sound waves, plasma waves, electromagnetic waves that can get created at the surface of the sun and then driven out into the corona. And those might drop enough energy off there to create, make it really hot. In general, the flare heating model is the one that most people subscribe to. The current issue with it is that while we see a lot of energy go into the sun's corona, we don't see enough energy from flares going into it. And the problem is the fact that it's really, really hard to see small flares because the sun itself is so bright. To see these little explosions happening is really difficult to do. If we could, we suspect that we would see several of them. They would actually be the primary heater of the corona. We just basically lack the sophisticated instruments to see these really tiny, what we call nano flares happening on the sun. That is sort of the next stage of high energy solar physics, is we want to create instruments that can actually see these really faint energetic sources on the surface of the sun. With that, we should probably transition to the activity that Hayley will be doing. So thank you for all the questions. If there are more questions at the end and you want to stick around, I will be happy to answer more of them. It's just that we allotted 60 minutes for this this whole program. We're gonna make sure that we actually get to that activity. So thank you for your questions. We will try to answer more later on, but now I will hand it over to Hayley.
All right, hi everybody. So I'm going to talk a little bit more about the space weather that Trevor mentioned, about coronal mass ejections and solar flares and how we see those and measure them from Earth. So the first website that we're going to look at is called HelioViewerorg. So I'm going to go ahead and send that in the YouTube chat. Hopefully you guys can see it. Actually, apparently I'm not allowed to send links in the YouTube chat.
Do you have moderator status?
But if Laura, if you could send HelioViewerorg into the YouTube chat, then we will take a look. So I'd encourage you, if you want to follow along with me on the website. Otherwise, feel free to just watch because I'm going to share my screen. And this is a good website to go to anytime after the talk. So let's see. All right. So hopefully you guys can see HelioViewer.org open on my screen. So what you're looking at right now is a close to live, actually, picture of the sun that was taken by the Solar Dynamic Observatory that Trevor mentioned earlier. So this picture was actually taken only like 20 minutes ago by this observatory. So at any time, if you go to HelioViewer.org, the first thing that it should show you is the kind of most recent data of the sun that we have. If you go to the left and click on data sources, you can see tons of options. We're going to talk about a few of them and how to work them. Right now, you can see in green here the current time that we're looking at. So that was only like half an hour ago that this data was taken. You can see the observatory, SDO, Solar Dynamic Observatory, the instrument that was used, the wavelength that we're looking at. So this is 304 angstroms. So that's kind of the color of light that we were talking about earlier. And this particular wavelength actually you wouldn't be able to see with your eyes. It's in the ultraviolet. So the color that shows up on the website isn't necessarily the color that wavelength actually is, because of course we can't see ultraviolet light, so we just have to come up with a color to look at. So right now, you might notice that there's a few, spots of light on this image of the sun, but overall it's fairly constant in what it looks like. And that's because solar activity, like solar flares and sunspots, actually take place on an 11-year cycle. So every 11 years, we see in the middle of that cycle a maximum in solar activity where there's tons and tons of sunspots and solar flares. And then at the end of that 11-year cycle, there's a minimum where there's not a lot of solar activity. So right now we're close to the minimum of the solar cycle this year. So we're not seeing a ton of solar activity. If you were to look at the sun right now with a telescope with a solar filter, you would not be likely to see a lot of sunspots. And one way that you can also view the sun on HelioViewer is not just through what it looks like in light, but what the magnetic field of the sun looks like. So what I'm going to do is click on Instrument and change to HMI, and then change from Continuum to Magnetogram. And what you're seeing here is the magnetic field lines of the sun in these, I'm going to zoom in a little bit, in these light and dark areas on this image. So anywhere you see a light area, I believe that's magnetic field lines in the sun pointing out, and the dark areas are where they're pointing in. So as you can see on this image, there's not a ton going on. There's just a few little speckles, but overall, again, it's a very consistent image. So something cool that you can do with HelioViewer is that you can go back in time and see what the sun looked like on pretty much any day for the past, I'd say 30 years. So we're going to look at a date that had a little bit more solar activity going on, so you can see the difference. So I'm going to switch back to AIA and switch back to 304. So again, this is the sun right now, but if I go up to observation date on this panel and switch from 2020 back to 2012, 2012 was a year that had a lot more solar activity than 2020 does. So Trevor actually mentioned the giant solar storm of 2012 earlier, and that occurred near the end of July. So I'm going to click on July 30th, and the image will load. And hopefully you guys can see how much more activity now is going on the sun. You can see these really big, swirling, bright and dark areas. And so compared to what we were seeing before, you can tell just with this picture how much more activity is going on the sun. There's more sunspots, there's more solar flares happening around this time, and definitely more coronal mass ejections. So Trevor mentioned that the coronal mass ejection that happened right around this date, I believe it was July 23rd of 2012, was one of the biggest coronal mass ejections that we have ever measured. And it got extremely close to hitting Earth, like just passing through the atmosphere almost. So if that would have hit Earth, as Trevor mentioned, we could have seen massive power outages and huge damage to electronics. So it's a very good thing that it didn't quite hit Earth. And then if we switch now again, so I'm switching from AIA to HMI, from continuum to magnetogram, you can see how much more activity is going on in terms of the magnetic field lines of the sun. I'll zoom in again. You can see these areas where the black parts and the white parts are really blending together. That means that there's a lot of magnetic field lines pointing in opposite directions, all bunched up together. And that is what really causes these massive solar weather events. So anytime that you see areas like this where things are mixed together in terms of the polarity, as we would say, of the magnetic fields, then you can predict that there will be sunspots there and there will be possibly solar flares and coronal mass ejections. So I think somebody had asked in the chat that we didn't get to about whether or not we can predict solar flares or any type of space weather. And the answer is that we definitely can, because we're always measuring and looking at the sun to predict these things, not only for purely scientific reasons to study it, but also because we want to be able to protect ourselves in the event of some giant solar storm. So another thing that you can do with HelioViewer is you can see down here on this tab, features and events, and you can go ahead and click on and have active regions pop up or sunspots pop up, and it'll show you exactly where they are. If you click on them, it'll give you a little bit of information about the time of that event. So there's a lot to play with here, and if that is relevant to the image you're looking at, you'll see it light up. You also see coronal holes, these large sections. There's a hole in the corona. So all of this is observable on this website. I think it's really cool to be able to see exactly where all of these events might be taking place. I'm going to go back even further in time now, show you guys another cool date. So there was a giant solar storm on Halloween in 2003. So I'm going to 2003 on this observation date selector and going to October 31st. And then I'm going to switch. If you notice in red here, where it says the date of what the image is, it actually says 2010. It's obviously not the same as 2003. And that's because the SDO observatory was only launched in 2010. So we're not going to be able to see anything from 2003 if we look at that observatory. So I'm going to switch this to SOHO, which was launched a little bit earlier. And now I'm able to see the sun on Halloween of 2003. I'm going to switch to the same wavelength we were looking at earlier, so it's easier to compare. And you should be able to see how much activity was going on that date. So there's a lot of, if you look, I believe on Wikipedia, you can find a pretty good list of like active dates of the sun if you're interested in looking at cool times on HelioViewer. And of course, you can always change the wavelength and see what it looks like in different colors, but just keep in mind that these colors are not the actual color of the wavelength, but rather just something to show you what it might look like. And another cool feature that I really like is this jump feature. So I'm actually going to go back to today, which I believe it should let me, July 2020. So going back to today and switching back to SDO, because that's the modern observatory. If I go to jump and change this to say 12 hours, I can make myself kind of my own little movie of the sun progressing through time. So we're going back in time throughout today in the past couple days, and you can see how much the activity on the sun varies over that time. So not only does the activity on the sun vary over the 11-year cycle that I mentioned, but it can also actually vary on a shorter time scale than that. So I would encourage all of you to look at this website. Maybe you want to see what the sun looked like on your birthday, or you want to see what kind of active regions are on the sun today. And this is a completely free website for you guys to use. And then another thing to look at in terms of space weather is the Space Weather Prediction Center the Space Weather Enthusiast dashboard. So I don't know if that link has also been sent in the chat, but if Laura, if you could do that as well. This is basically a live view of the current measurements and predictions of space weather, and more focused on how they might affect the Earth. So if we look at this little chart here, you should be able to see that all of these measurements, just by eye, are pretty low. And that's again because I mentioned that we're at the end or the beginning of a solar cycle, so there's not a lot of activity. So this top one is the X-rays coming from the sun, seems very low. The protons coming from the sun, that's kind of what we talk about when we say solar wind, that's very low. And also geomagnetic activity that's caused by the solar wind is very low. If we scroll down, we have another, I'm not going to talk about all of these. The coolest one, in my opinion, is this WSA Enlil prediction, which I'm not actually sure what that stands for, but essentially what you're seeing is a modeled prediction of the next few hours of, or maybe longer than that, of what the solar wind actually looks like. So when I press play, it might take a second to load. On the top, you're seeing the density of the plasma coming out of the sun. At the bottom, you're seeing the velocity of the plasma coming out of the sun. And then the little green dot right here is Earth, while the yellow dot is the sun. So again, this is a prediction based on what we're seeing, the current data from the sun of what the solar wind will look like, which again is really important for us to have so that we know potential problems for power grids. And then on this, so you can kind of see a side view on this side of what it might look like with the Earth. And I think this one's pretty cool down here because you can kind of see exactly how the Earth's magnetic field is protecting us from the solar wind, because you can see how much slower it is as it goes around the Earth. Some other cool things in here I would encourage you, I think we're kind of running out of time, but I would definitely encourage people, if you're interested, to check out this website and explore the different options, especially if you're interested in space weather. And then this is the cycle I mentioned. You can see it every 11 years repeating. And here we are right at the bottom, not getting a lot of activity. That's pretty much all I have. I don't know, Trevor, if you have anything else you want to add.
Yeah, so the thing I want to specifically add is that these aren't, special, images for the public that are made. These are the actual data, the actual models that space physicists use. The HelioViewer images that you see from the AIA, I've used those images in my own research. So it's the exact same thing. So a kind of a cool thing within the solar community is that all of our data is generally immediately accessible to everyone in the public. And it's kind of because, as you're seeing with the space weather dashboard, the sun has a direct and important impact on all of us. And so we are always keen on sort of letting anybody sort of examine the sun, see what it's doing.
Do we want to answer some more questions if people are sticking around?
Yeah, so I am perfectly okay with staying around. I want to thank everyone for coming to this event. We're at 9:02 p.m., so we understand if you're unable to stay with us longer. But I'm perfectly happy to answer more questions.
Great. Well, we have some more questions. We have a question here that asks, what is the closest that any spacecraft has been near the sun?
So that would be the Parker Solar Probe. It is currently undergoing its science mission as it orbits the sun. And its closest approach is on the order of about 10 solar radii. And so that, if you consider how big a solar radius is, it might not seem like it's very close, because the sun is a very large object. But because the corona, that sort of sparse thing that I showed you earlier, such a hot and sort of energetic thing, is very, very close to get any close. It's very, very difficult to get any closer to the sun. So about 10 solar radii, which corresponds to about 7 million kilometers.
There's a later question that follows up on that from Ashwa, asking if that is within the orbit of Mercury. It has the Parker probe past Mercury, basically.
It's certainly gone well within the orbit of Mercury, much closer. The solar orbiter is actually going to have a orbit that's relatively similar to Mercury, and Parker Probe has gone, much closer to that. In terms of did it go by it, not particularly, because it wasn't a mission designed to try and see any planets, other than maybe using them at times to create what's called a gravitational assist. And so in an astronomical sense, it kind of got close to Mercury, but in a more literal sense, no, not really.
Ashroth also asks, as of today, are there new sunspots discovered?
So the sun is constantly sort of evolving. And you can actually go to something like the Helioviewer and see, are there any sunspots right now? I believe currently the sun is very, very quiet, which is sad for somebody like me who likes to study energetic things happening on the sun. But I believe we are right now in a pretty quiet phase of the sun. I do not believe we have any major sunspots. It doesn't look like it.
But if we were in a more active period of the solar cycle, then we would be discovering new sunspots very, very often, because in those more active periods, there are lots of them that do show up.
We have another question that asks, how refined are the current models for the layers in the sun's structure?
So that's an interesting question. The way that we model the sun and other stars is we use supercomputers that use these really complex equations to sort of figure out all of these different physics that are happening, and they're really, really intensive. So they use, these computers that have so many processors to actually calculate them. In terms of the atmosphere, things are a little simpler, and so the different models that are used are all sort of managed and operated by SWPC, the Space Weather Prediction Center. Um, and they're vary a lot in terms of their detail. Some are really, really complex, but the more complex you are, the more computationally intensive it becomes. So you need a more powerful computer to be able to actually process those models. And so SWPC, Space Weather Prediction Center, uses all kinds of models to actually sort of predict and observe what's happening on the surface of the sun. A scientist like myself, they might use something that is really, really intensive to model sort of a very small section of the sun. Because we aren't so interested in knowing, what's happening tomorrow as we are about understanding what is the underlying physics that's driving all of these really interesting, explosive, energetic events.
And we have another question here. From Franklin, who asks, does the sun grow every year?
That's an interesting question. So the sun doesn't really pick up more mass every year. It does sort of suck up dust and comets and things, but the amount of mass that it is adding on is really insignificant. The sun is, however, slowly expanding, and that is due to the fact that in the core of the sun is fusing the element hydrogen into the element helium. And the sun is not currently hot enough to fuse helium into carbon. So what we have happening in the core of the sun is all this what we call helium ash building up. As helium ash builds up, the part of the core that is sort of undergoing fusion gets bigger. As it gets bigger, it's staying the same temperature, it gets hotter, more energy is coming out. That's causing the sun to become brighter. Solar brightening is ultimately a very, very small thing. It's not something that you can really notice on year to year, but over the course of hundreds of thousands to millions of years, it can become a appreciable difference. So it is getting bigger, but it's only because of what's happening on the inside, not what's happening on the outside.
Should we continue taking questions? How many more would you like me to ask?
How many more are there, I guess? It looks like there's only a
Well,
few
we've
more.
got a long list of questions. They keep going.
Okay, well, yeah, I guess we can do, say 3 more questions and then to call it a night.
Okay. So Chris asks, how do the astronauts on board the International Space Station protect themselves from a large solar flare or coronal mass ejection?
So when these events happen, they are oftentimes just large clouds of these really energetic particles that are coming from the sun and going to hit Earth. People in the International Space Station, because they're outside the atmosphere of the sun, the Earth, they're kind of not as well protected. And so the way that they actually protect themselves is they don't go behind pieces of metal; they go to where their water is stored. So water is a relatively dense fluid, and it can do a really good job of absorbing energetic particles and sort of stopping those particles from sort of creating particle showers. So what they actually will do is they'll go to their place where they store water, which are stored in these large sort of bags. They'll basically just surround themselves in bags of water until the space weather event is over.
We have another question here from Olivia, who asks, what gases are stars made out of?
So the primary element that stars are made of is called hydrogen. It is the lightest element in the universe. It is the most abundant element in the universe. And so, what many stars do, though, is they will take hydrogen and they will fuse it into helium, which is the second lightest element in the universe. And then from there, they can fuse it into more elements like carbon and oxygen and going up. So, for small stars like the sun, they are predominantly hydrogen. Over time, their cores will become helium, and then further on, they'll become carbon and oxygen in the core. Still, and with that happening, the majority of the star will remain hydrogen. For really, really big stars, like those O and B class stars I talked about at the beginning of all of this, those can actually fuse elements all the way up to iron and nickel, which are very heavy elements. But still, even then, the majority of the star will remain hydrogen. Even to this day, it's estimated that about 75% of the baryonic matter in the universe is still hydrogen.
And this last question is also from Olivia. She is 7 years old and she is interested in becoming a space meteorologist and would like a little bit of guidance into how to get started on that path.
Well, there are a few ways of actually doing it. So after you graduate high school, you'll want to try and major in something like physics, astronomy, or actually atmospheric sciences. So when I took a visit to the Space Weather Prediction Center, I spoke to various space weather meteorologists. Um, one of them, ones I talked to, actually started out as a meteorologist in the Army or the Air Force, and from there, he sort of didn't want to be in the Air Force anymore, but he had sort of the skill set. He found out that he could actually apply that skill set into space weather really easily because the fundamentals of how they do their job, you taking these models, you're applying them to this data, you're making predictions based off of that, is really very similar. Um, you can also go into learning about space weather from the research side, in which case you want to, after undergrad, so getting your degree in physics or astrophysics, go into graduate school and pursue a PhD, which is what we're all doing. Specialize in looking at space weather and space physics, sort of figuring out things that are related to um, those fields. So it takes a long time. It's a lot of studying, but if it's something that you're interested in, then it's certainly something that you should pursue. All right. unfortunately, we're going to have to call it there. I guess unless there are only a few more questions. Look at the chat now. Looks like we have.
No, we have several more questions.
Did you skip some
But
earlier?
yes, we have quite a long list here of questions, and I apologize to those who were not able to get their questions answered tonight, because there are quite a number of them actually.
Okay. All right. Well, I guess once again, I'd like to thank everyone for attending this event tonight. If you go to the Universe at Home webpage, which is on the Minnesota Institute for Astrophysics website, you can see a schedule for all of the events that will be happening in the future and sort of what they are, what the activities will be. I believe we are trying to target doing one every Wednesday from here throughout August. So there'll be several more talks, ranging from a huge variety of topics about space and astronomy. And so if you enjoyed tonight, please feel free to go onto that website and register for more events in the future, and we would love to see you there.
Yeah, thanks everybody for coming. Thank you for your questions. I hope you learned something tonight and come back and see us again next week or throughout the rest of the summer.